Okay, let's start. We're just going to pick up where we left off. We are doing trig integrals, and we're looking at if we want to integrate sine to the m of x, cosine to the n of x. We did cases. The last case, I think I mentioned this, but I didn't actually deal with it, is if both m and n are even. And the strategy for this one use the half angle formula. To break down the powers. So we did it when one was odd and one was even, and the idea was whoever was odd, you kind of save one of those factors and you use the Pythagorean identity to change all the other guys into the other trig function. If they were both odd, you save the lowest one, save a factor of the lower power, because it will prevent you from having to use the Pythagorean identity and expand something larger. And the last case was if they're both even, we just use the half angle formulas. So you might remember what those guys are. This is referring to the formula that sine squared x is equal to 1/2 1 minus cosine 2x. And cosine 2x we know how to integrate using substitution pretty well. Also the cosine of x, cosine squared is 1/2 1 plus cosine 2x. And that's just basically us taking the double angle form for cosine and rewriting it. You get that guy. Those two identities. These are called the half angle formulas because this angle is half of that angle. Okay, so example one, simple example, let's say we wanted to do sine squared x. Then this is just equal to 1/2 times 1 minus cosine 2x dx. This is going to be 1/2 times x minus, this would be a half sine 2x. That's not bad. But it's completely fine to leave it like that. You could multiply out if you wanted to, but I wouldn't really care. To me, that's fine. So that's how you deal with an even power. Let's say we had two of them. We actually have a couple options here. Perhaps more, it depends on which trig identity you want to apply. But there's two options, is to first use the double angle formula for sine. We know that sine of 2x is equal to 2 sine x cosine x. Which means that if I take half of sine 2x, this is equal to sine x cosine x. Which means I could square both sides. And I know with that guy, I can actually rewrite it in terms of a single trig function, the sine function, and it would be squared. So I could say that sine squared cosine squared is going to be equal to 1/4 times sine squared 2x dx. Then I would apply the double angle formula for sine squared, except instead of x I have 2x, so over here I'd have 4x. And so this would be half 1 minus cosine 4x dx. So that would give us 1/8 times x minus. That was one option. I think that would be the easier option here. You could go do the other option and just apply the double angle formula to both parts. And then that would lead you to multiply out and figure some things out after that, but it's doable. If you don't see that, then this way you can see, and it'll take you a little bit longer, but it's still not bad. You know, so if you have sine squared you could apply the double angle formula to each of these, so I would end up with a quarter out here, and then this would be 1 minus cosine 2x times 1 plus cosine 2x. And then I of course expand these. It's 1, but this is of course like the difference of squares, so this would be 1 minus cosine squared 2x. You get a squared minus b squared. And then you can apply the half angle formula to the cosine squared. Or you can also notice that 1 minus cosine squared is sine squared. So you could have even gotten back to here, realize that this is sine squared 4x. Well, you would have continued like that, so I'm not going to do that. I'm just going to actually brute force through this. So this would be the integral of 1 minus a half 1 plus cosine 4x. This would be a half minus a half cosine 4x. This would be a half x minus an eighth sine 4x. So as with all these trig functions, sometimes you'll have several options. You can apply different identities. You can get to the answer anyway. Notice here that if I did multiply out, I would get exactly the same thing. You should be aware that with trig functions, it's possible to get answers that might look different, but they are actually all valid answers. So let me give you an example of that. Let's start over here. We're kind of rushing a bit because I really want to get to trig substitution today. That's the main thing I want to do today. But if I'm moving too fast, you can just stop me. So sometimes, and this is true in general, but it's more true with trig functions because there are a bunch of identities that you can use. Sometimes we can get different looking answers by using different identities. If that's the case, don't worry. They can all be valid. They will just differ by a constant. You you can always check by differentiating your answer. And yeah, don't worry if you did a method other than I did in my solutions, I will figure out that you have the right thing. But just be aware that this is a potential issue you might face, but it's actually a non-issue. You don't have to worry about you're doing something wrong. Let me give you an example with just sine x times cosine. There are a bunch of ways you can do this. For one, I can do a substitution. U equals sine. This would mean my du is equal to cosine. And so basically this would become the integral of u du, which is equal to u squared over 2 plus c. So that would give me sine squared x over 2 plus c. And you can check if you differentiate this using the chain rule, you will get that. Another student might decide to do u equals cosine. And that is also a valid thing to do. Your du would give you a negative sign though, negative sine x dx. And so you end up with negative u du, which is negative u squared over 2 plus c. So this would be negative cosine squared x over 2 plus c. And so they'll get an answer that looks different from yours, but all you need to remember is that sine squared plus cosine squared is 1. And so technically, this guy here is actually equal to 1 minus cosine squared x all over 2 plus c. So that's really equal to a half minus cosine squared x over 2 plus c. And then this half, I can kind of absorb it into that plus c. And so it really ends up being the same thing. Right? It's really the same, even though it might initially look different. Right? It just depends on the identity that you invoke in the first place. You can look like different answers, but they're all valid. If you differentiate either of these, you will get that back. And notice that these answers can be reconciled because you can show that the difference between them happens in that plus c. Right? There's, again, still another way you could have done this. You could have invoked the fact that sine 2x is equal to 2 sine x cosine x. So this would mean 1/2 sine 2x is equal to sine x cosine x. And so the integral of sine x cosine x is equal to 1/2 the integral of sine 2x dx, which is going to be equal to minus 1/2 cos minus 1/4 cosine 2x plus c. And again, that looks different from this. It also looks different from this. But then you just remember, what is cosine 2x? It's actually just cosine squared minus sine squared. So it's actually just a sum of these two. It'll differ by a constant from the other answers as well. So potential pitfall, you might be practicing and you might look in the back of your book on some of these answers, and the answer in the back of the textbook will look very different from your answer, and you might freak out. There's no need to freak out. It's perfectly valid and normal and natural for these things to happen, and it doesn't mean anything is wrong. If you ever are in any doubt as to if your answer is the right answer, just differentiate it. You can differentiate all of these with the chain rule pretty easily, and you'll ultimately get back to that. Let's look at another set of functions. Secants and tangents often come mixed together. So secant mx times tangent nx. So of course the idea here is to use, we have an identity that relates tangent to secant. It's one of the Pythagorean identities. So we know that, what is the identity? It's 1 plus tangent squared is equal to secant squared. Right? Or you can use the fact that tangent squared is equal to secant squared minus 1. So basically, you're doing the same idea with sines and cosines, except with tangents, you just have, you're applying this formula. So again, we have 4 cases. M odd and even. Odd. Did I have an example for all the cases, or did I think it's too redundant? Okay, I did the even case for secant, the odd case for tangent. This one does get a bit tricky. Where m is even, it should be 2. And m is odd. Okay, so let's do some examples here. Secant to the 4th and secant to the 4th times tangent squared. Let's run through those. So, examples to cover. This will kind of cover whenever secant is even. 2 and 4. I'm going to do 2 examples here. Secant to the 4th x and secant to the 4th x and square x. And the main idea here, power of secant is even, save a factor of secant squared, change all other secants to tangents using that secant squared x is equal to 1 plus tangent squared x. Then do u equals tangent. So that's the basic idea here. So for example, power of secant is even. The power of tangent is also even here, by the way. The power of tangent is 0. So what we do is you save a factor of secant squared. That's the guy we're saving. That's going to end up being our du. We're going to change all of the secants to tangents using that identity. There's 1 plus tangent squared. And then we do u equals tangent. Our du here is going to give us that secant squared. And so this would just become the integral of 1 plus u squared du. And this will just be u with tangent. Questions on that? I'm going pretty quick, but the procedure, the strategy is pretty much the same as with sines and cosines. It's just that you're using the other Pythagorean identity. If I had secant to the 4th times tangent squared, or this could be any other power of tangent, it could be tangent cubed, whatever, you'll just multiply it out. Then I'd leave this as secant squared times tangent squared, and put my secant squared at the end. Change all other secants to tangents, that's 1 plus tangent squared times tangent squared. And I'll get in there plus tangent. U squared times u squared dU. This is u cubed over 3 plus u to the 5th over 5 plus c. And our u is tangent, so it's tangent cubed x over 3 plus tangent to the 5th x over 5 plus c. And that would be your antiderivative. I don't remember the cases, but let's do an example about when power of tangent is odd. Yes. Here, the secant is present. We'll talk about it. Here you save a factor of secant tangent. Change all other tangents to secants. Do u equals secant. We do 2 examples. Secant tangent cubed and secant cubed tangent cubed. So here you have secants and tangents, and the power of tangent is odd. So what we do is, I'm going to leave a tangent squared right here, and then I'm going to factor off a secant x tangent x. And that's going to be my du. And the idea now is once you factor off an odd power of tangent, you'll have an even power left, so you can use the Pythagorean identity. So we know that tangent is secant squared minus 1. Derivative of secant is secant tangent. So this just becomes u squared minus 1 d.
Before you start the next one, can you just give us a second to copy that down so we can follow along?
Okay.
Thank you.
I'm not going to have a lot of time to talk about trig stuff. I want to get to I'm going to teach you trig stuff and then you're going to hate it. Like, I hate it. I still hate it. I hate it. I avoid it whenever I can, but sometimes you can't avoid it. You guys uncopied?
Yeah.
By the way, I think our next test is going to be also soon. It'll probably be in about 2.5 weeks for the second test. So what was my other example? When does spring break start?
21st of March, I think.
It's the 22nd to the 3rd.
Oh, sorry. Yeah, 21st is the last day of school.
Yeah. And then
Okay.
we resume the 3rd.
We leave on a, what, Thursday, right?
I think Wednesday is the last full day of school.
Yeah, yeah. So we can do it on
It'll
Wednesday.
probably just before you leave on spring break. Or leave it after. I don't know what you guys want to do. If you want to be on spring break worrying about your calculus exam, everyone's like party. You're here in the corner, like trying to remember what the integral of secant is. Isn't cute? I can't remember what the integral of secant Q. You're crying in the corner. Okay. Again, here we know that tangent is odd. So you kind of put a secant times tangent at the end. So du. You'd be left over with secant squared, tangent squared. There are some weird situations with secants and tangents, but we'll get to that soon. Yeah, so because that's my du, it means I only want secants over here, so I'm going to change that tangent. So this is secant squared x. Tangent would be secant squared minus 1. So I'm going to u equals secant. We'll do trig sub tomorrow. Yeah, for secants and tangents, other cases can actually be tricky. And they can involve a lot of other techniques. So you might have to do integration by parts, or all sorts of things can show up here. And I'll talk about a very important integral in this section. That you want to do it once, integration by parts, and then memorize the form from then on, because it's something you'll never want to do again. But we can take advantage of the fact that we know that the integral of tangent by itself, do you remember what that is, integral of tangent? I did that in Calc 1. It's not that bad. The trick here was to just write it as sine over cosine and then do like a u equals sine. Well, so if you never did ln's in Calc 1, you probably never did it. So let's actually just do it. So here's just when you have a tangent to an odd power and there is no secant. This trick obviously can't work because there's no secant to factor out. So the trick here was to just actually rewrite it in sines and cosines. Every so often, if you can't see a trick to deal with the weird trig functions that you have, switching to sines and cosines might be an idea, might be an option that you want. So here what we would do is u equals cosine, so du equals minus sine. And so the integral just becomes minus 1 over u du. So this is just minus ln of u plus c. So it's minus ln of cosine. That's also equivalent to saying ln of secant. If you don't like that sign, the negative sign out in front. The idea is because it's a log, you can take that minus 1 and move that power up. And cosine to the minus 1 is secant. So you can remember either of those formulas. There's another weird formula. There are a couple like this, but we'll only really focus on one. Cosecant is the other guy that has a weird formula like this, but secant, the integral of secant has a weird formula.
I have a question.
Yes.
Why is it 1 over u?
My u is cosine, so my cosine is in the denominator. So here, this guy just becomes minus du, and then I have a u in the bottom. So it's minus 1 over u. And that gives me ln. And so this is just another rule you can know at this point. So the integral of tangent is ln of secant. Worth memorizing. Integral of secant also worth memorizing because figuring out is actually not that straightforward. The calculations are straightforward in hindsight, but why would anyone even think of doing this in the first place would be kind of baffling, I guess. It was baffling to me. So the trick here is you actually multiply and divide by this weird thing. Do any of you know this trick, or you've seen it before?
No. Yeah, you
see-
multiply by secant x plus tan x over secant.
You actually multiply by secant x plus tangent x divided by secant x plus tangent x.
That's very good.
So someone just thought of that, but here's why that works. Here's why it's genius. Notice that now if I multiply across, this becomes secant squared plus secant tangent over secant x plus tangent x. And what's the derivative of tangent? Well, it's secant squared. And what's the derivative of secant? Well, it's secant tangent. So by multiplying by this, you get that the numerator becomes the derivative of the denominator. So what you do here, because I was sick, I was out of the gym for a while, so yesterday I finally started working out again, and now I'm like, I'm sore all over. It was so much painful to pick up that eraser just now. Okay. So you do u at this point is equal to secant plus tangent, and your du would be secant x tangent x, plus derivative of tangent is secant squared x. And that happens to be the entire numerator. So this just becomes the integral of 1 over u du. So that leaves us with ln of u plus c. And so this gives us ln of secant x plus tangent x plus c. So in other words, the integral of secant dx is ln of secant x plus tangent x plus c. Memorize this one. There's a similar trick used to find the integral of cosecant, but don't memorize that for now. If you can deal with secant and tangents in principle, you'll be able to deal with cosecants and cotangents using exactly the same principles. So I'm really going to focus on secants and tangents, and so I want you to memorize the formulas for those. The cosecant and cotangent equivalents, don't worry about it. I assume if you ever encounter them in your classes, you'll be able to just look up the integral rules and you'll know how to juggle them if you know how to juggle these very well. So the other cases for secants and tangents, they can be tricky, but using these two integral formulas can come in handy. And it can get pretty here. So example, the famous, should I start with this? Hey, let's do it, let's be real. Secant cubed x dx. Now that's a very weird function because it just naturally pops up over the word. It's kind of like the e of trig functions. So there are many other applications that when you take higher math classes, at some point you're going to do something and you're going to end up having to integrate secant cubed. It's actually worth memorizing, but let's actually derive it. So it's actually a very famous example to do here. So you'll notice because there are no tangents present, you can actually use the Pythagorean identities. So you have to be a little more, you have to have a little bit more ingenuity similar to what you had here. But this guy is actually, it's going to be a lot trickier than it might appear at first. So to integrate secant, this is what you do. To integrate secant squared, you know that the answer is just tangent, that one's easy. To integrate secant cubed is actually pretty, yeah.
So you can only use the Pythagorean identities if you have secant.
If you have both the secant and tangents, because then you can chain one into the other.
Okay,
But if you only have a tangent or you only have a secant, then it's kind of, it's weird.
okay.
So let's just call this I is the integral of secant cubed. So here's the way you do it. The first trick is to actually break this up into secant squared times secant. And what we're going to actually do at this point is we're going to try int by parts. Now, both the pieces in the by parts are trig functions. So what do you think you would do here? What would be the u and the dv here?
U was secant squared x, because it has the square, so algebra.
Think ahead what would make your life easier. If you said u is this, then when you differentiate that, you need the chain rule. You'll get a tangent popping up. It seems to make things kind of hairy at the beginning. Whereas if that's your guy that you want to integrate, then it's just a single tangent by itself. It actually looks easier to deal with. And you can probably piggyback on one of those rules. The integral of secant we also know because we just derived it. So the standard way here is to actually do u equals secant, and your dv equals secant squared. Yes. So your du is secant tangent, your v is just tangent. And so now we're going to use the integration by parts formula. So we know that I now is going to be u times v minus the integral of v du. So that's secant x tangent x minus the integral of secant x tangent squared x. And so now the hope is dealing with this integral should be easier than dealing with that integral, because now I have both the secant and tangents playing together. I can probably figure something out. But the derivative of tangent is not odd, so I can't do that trick where I just factor off a secant tangent. And the derivative of secant is not even, so I can't do that trick where I factor off secant squared. So what we do here is we kind of invoke the Pythagorean identity to try to make it look different. So I'm just going to throw in the fact that tangent squared is equal to secant squared minus 1. And so what we end up with is the integral of secant cubed x minus secant x. Someone saw it. There's your secant cubed showing up on that side. That guy here is I. And so remember though that this secant is still in the integral. So I'm really going to split this integral into two parts. So this is equal to secant x tangent x minus I plus the integral of secant x. So this would mean, take this I to the other side, 2I is equal to secant x tangent x plus the integral of secant x dx.
Why is it 2i?
Because the
Oh,
minus
because
sign.
you already had
There's
the-
a negative sign here, and there's an
Oh,
I on
okay.
that side, so I bring it over. Which means that my I is going to be 1/2 times, now I'm going to put the integral of this guy. That guy's just secant tangent plus the integral of secant we just derived is the ln of secant x plus tangent x. This is worth memorizing. Integral of secant cubed x dx to 1/2 secant x tangent x plus ln of secant x plus tangent x. It's probably one of the longer formulas that we'll be memorizing during the semester, but it shows up often enough for you to memorize it. Yeah.
So now secant to the 5th x, right?
You can do that. I think in your homework you have a bunch of other examples, but we're sort of over time, so we'll stop there. Talk a little bit more about this next time, and then we'll jump into trig substitution, which is just a variation on substitution, but we're using trig functions.
Professor,
Yeah.
so just to confirm for the test tomorrow, it's going to be during the recitation.
Recitation during the whole period. You'll have the whole period for the test.
And it's going to be through 6-8,
Come in?
6.8.
Yeah, everything before we started integration by parts. So the review is a good guide. So just go through the review and it should give you a good idea.
Right?
Huh?
That's what we use.
No, recitation during recitation.